This season of Threshold is underwritten by the Pulitzer Center on Crisis Reporting.
Back in our first episode, I told you that I fell in love with the Greenland ice sheet. Welcome to Threshold. I'm Amy Martin, and I actually think the seeds of that love affair might have been planted when I was a little kid, looking at our family globe. I remember seeing this big white island hanging out between North America and Europe and thinking, what is that place like? But it wasn't until I started my reporting for this season that I got my first glimpse of it. I was on a flight from Denver to Stockholm. The plane was dark, everyone else was sleeping, but I saw something bright trying to leak in under the bottom edge of the window shade. So I opened it, and there it was, the Greenland ice sheet, one of two major ice sheets remaining on the planet right there below us, shining in the Arctic sun. This massive piece of ice is so important for so many reasons. It holds precious information about the distant past. It's a big part of our climate future. But all of that sounds so clinical. I think the Greenland ice sheet is one of the wonders of the world. Even though it looks flat, at its highest point, it's more than 10,000 feet tall, taller than many mountains. In fact, that's kind of what it is, an upside-down mountain of ice. But there's no mountain this big on Earth. This thing is the same size as the state of Alaska, and it has snowflakes locked in its belly that fell from the sky more than 100,000 years ago. Everything about it is fascinating to me. I'm pretty sure my seatmates were annoyed that I had the window shade open on that plane ride, but I was like, no way am I going to close this right now. We were just starting our reporting. I didn't know yet if I was going to be able to go to Greenland, so I just sat there and stared at it, and when we passed over it, I craned my neck, watching it recede behind us, until finally I had to give up. I turned back around, closed the window shade, and fell asleep, wondering if that might be the closest I would ever get. But as it turned out, it wasn't. This is what it sounds like to walk on one of the two great ice sheets remaining on Earth. I made it to the Greenland ice sheet, and that's where we're going to spend this episode of Threshold.
We understand the basic science here. We have got this nailed down. Climate change is real, and it is us.
And what happens here should be of concern to everyone, no matter where they live.
So I feel like it's every geoscientist's dream to get to go to Greenland and to be able to see it with your own eyes.
Sea level rise has the ability to completely destabilize the status quo of the world.
It's all about the rate. We know what the number is. It's 7 meters. How fast can we move that into the ocean?
I'm flying in a helicopter with 3 students and 3 professors staring out the window at the Greenland ice sheet. And it's not just a big blank slab. It's a highly textured surface with bumps and cracks and serpentine blue rivers running across it. The helicopter touches down and the pilot opens the door, welcoming us to our home for the next 5 days.
Should I go ahead and hop out?
Yeah, go ahead.
As soon as we climb out, we're battered by gale force winds. We unload quickly and the helicopter takes off, leaving our little crew of 7 huddled together around our gear. We are the only splotch of color out here. It's ice as far as we can see in all directions.
So here's the plan. We're going to set up our personal tents. Everybody gets a tent, a piece of white foam, and then this big Paco pad that goes down.
This is Joel Harper, a glaciologist from the University of Montana, and the person I had somehow convinced to let me come along on this scientific expedition. It's a clear day, but storms can roll in at any time, so setting up shelter is a priority.
The key to setting up your personal tent is do not let the tent blow away, or you will be never seeing it again and cold for a while.
When I was trying to persuade Joel to let me come on this trip, one of my arguments was that I am outdoorsy. I like to camp, I like to backpack, he wasn't going to have to baby me. So when he hands the students and me an industrial-sized drill and a bundle of bamboo pieces taller than we are and tells us to go set up our tents, I try to play it cool, even though I have no idea what I'm supposed to do. I mean, I've set up a lot of tents in my life, but bamboo? And then there's the question of picking a good tent site, which is a little puzzling when you're camping on water. Granted, it's mostly frozen water, but it's not totally frozen, at least not in July when we were there. This part of the ice sheet is actually pockmarked with shallow holes. Some are pencil thin, some are large enough to lose your foot in, and they're all filled with freezing cold water. The wind makes it really hard to talk, so the four of us just sort of wander around on the ice, zombie-like, until I finally break down and ask for some guidance. I'm going to fast forward through the rest of the process and just say the bamboo poles were tent stakes, the drill was for making holes deep enough to hold them, and we all eventually got our tents up. In a few hours, mercifully, the wind died down and I was able to take out my microphone. It's such an amazing looking surface, like it's not anything like a snowy field.
No.
It's also not like an ice rink or something. It's totally unique.
It's a pretty interesting surface with this honeycomb. I mean, half of what we're walking around on is not ice. It's hole filled with water.
Yeah, and I was just thinking when I was when I went off to pee, I felt sort of bad because I'm peeing on fresh water.
Yeah.
Like wherever you step, wherever you pee, anything you do, you're just like soiling fresh water. And it really struck me of this is such an amazing resource of fresh water when there's so many places that need fresh water.
Yeah, there's a lot of it here. If you took all this ice and converted it to water and added it to the ocean, sea level would come up 7 meters.
Whoa.
So that's how much ice is here. Quite a lot.
Wow. 7 meters is about 23 feet. Adding that much water to the ocean would displace millions of people, from Louisiana to Bangladesh to the UK. The good news is, Joel says we're not going to lose the whole ice sheet all at once. But the bad news is,
even if we get 2 meters, that's a big amount of water. That's a lot of sea level rise that the coastal places have to deal with. The question is, how much do we get in 100 years or 200 years? It's all about the rate. We know what the number is. It's 7 meters. How fast can we move that into the ocean?
That's what Joel Harper and this team of scientists are trying to figure out. How fast and through what combination of processes will this mountain of ice end up in the sea? It's an area of study called ice sheet dynamics. And the first step in understanding it is grasping that this ice is dynamic. It moves.
Yeah, it's flowing like a fluid. Ice is essentially, a giant fluid moving along.
As we sit here on it, it feels like land.
You can't tell you're moving at all, but we're actually moving to the west at about 110 meters a year. Yeah, when we get picked up by the helicopter, this camp will be in a different place.
Joel says 110 meters per year is the average speed. It actually varies a lot depending on the season or even the particular day and where you are on the ice sheet. And just like any other fluid, this ice moves from high to low. The ice sheet is fattest in the middle and then tapers out to the edges.
Well, the thickest part of the ice sheet's about 3,200 meters thick.
But we are camped over ice that's only about 700 meters thick. That's the difference between 10,000 feet and a little more than 2,000 feet, a significant elevation change.
Ice sheet motion is taking mass from the high parts of the ice sheet where it's relatively sequestered from contributing to the ocean. It's cold. It's a long way from the ocean. Ice sheet motion takes that ice and moves the mass towards low elevation where it either melts in warmer temperatures or calves off into the ocean.
The movement of the ice from high to low and the calving off of the ice into the ocean, that's normal. If you see a picture of a big chunk of ice falling into the sea, that is not in and of itself an image of climate catastrophe. That's what this ice sheet does. It moves, it melts on the edges, it breaks off into the ocean. But, and this is a big but, at the same time that it loses mass on the periphery, it gains it in the middle, or at least it has been.
Problem is we're having more mass loss than we are gain at the moment, so that's why sea level's going up. The mass of the ice sheet's going down.
As we warm the planet, we're knocking the balance out of whack here. We're losing more ice than we're gaining, and the ice sheet is getting smaller. And as it's become clear that the ice sheet is no longer a permanent fixture on the landscape, the question of how it moves and how quickly it can move has started to become incredibly important.
Yeah, this has been subject of big scientific debate. How fast can we do this from Greenland?
Joel says it's not too hard to figure out the correlation between warming and melt. Like, scientists already have pretty solid formulas for X degrees of warming equals Y amount of ice sheet loss. What gets tricky, he says, is calculating the exact rate of that loss.
And so that's where all of our uncertainty comes from in projecting the future of sea level rise from Greenland, is how fast can this thing move? How fast can this thing take mass from the central high elevation places and deliver that mass to the edges where it can be put into the oceans? That's why what we're doing really matters.
So how long before all of this ice ends up in the ocean?
I think the community's fairly well reached consensus that it's not a decade, it's not really even a century thing, that we can get all of it. I mean, it's 7 meters here. The question is, how much do we get in 100 years or 200 years?
So we're not going to just wake up one morning and discover that the whole ice sheet is gone. But we don't really know how long it would take to lose the whole thing. That depends on a lot of things this team is studying. There are all kinds of interrelated mysteries to solve. Is it more likely to melt at a steady pace or in pulses? What role does surface melt play? What happens if the ice sheet begins to break apart? Could a smaller section of it suddenly start moving faster and throw previous calculations off?
This is where the motion part that we're working on really comes to play.
Understanding all of this stuff matters because the speed of sea level rise has everything to do with how well people and animals and plants can adapt to it. And Joel says the potential sea level rise is actually only one of the reasons why this ice sheet is so important.
Ice itself is a big part of the climate system. Ice actually influences how the climate system works.
One of the ways it does that is through albedo. That's the reflective power of the ice that we talked about back in episode 7. Just like sea ice, the Greenland ice sheet is a really good mirror, bouncing solar energy away from the Earth back out into space. I could feel this happening. There was so much sunlight reflecting up from the ice that I got a sunburn on the underside of my chin and nose. That was a first.
You know, the Earth has constant heat coming in from the sun and heat going back out. But at the equator, way more heat comes in than goes out. So that heat moves through the oceans, through the atmosphere, to the poles, where way more heat goes out than comes in. So here's where we lose our heat. It's our pit zips.
I love it, yes.
This cracked me up because it's something only a glaciologist or a serious skier would say, and Joel is both. You find pit zips in a lot of winter sports jackets these days, zippers that allow you to open up the armpits and release some body heat. They basically help you keep your own personal mini-climate in the Goldilocks zone, not too hot, not too cold. And what Joel's saying is that the frozen polar regions provide that same service for the planet. They vent heat out of the Earth's climate system, helping to keep it in that just right range. But as we've been adding heat-trapping gases to the atmosphere, these polar pit zips can't keep up.
If we're piling in a lot more heat around the planet, it's inevitably finding its way to the poles, and this is where we're starting to get a lot of extra warming going on up here because it's accumulating here. The heat is traveling to the pit zip and it can't get out. Not enough.
Not fast enough.
It's piling up. Yeah.
And when the Earth's heat piles up at the pit zips, all kinds of things start to get weird. Weather, storms, ocean currents, the jet stream. That's why there's some urgency here, to get a better understanding of the processes that are transforming this big hunk of planet-cooling ice into water. And Joel says there are a lot of unanswered questions.
Yeah, we have a lot to learn about how glaciers and ice sheets move, the mechanics of motion.
That's interesting because in some ways it feels like movement is kind of one of those basic things we understand about a lot of things. Why don't we understand that about ice?
Well, look, we're standing on top of 700 meters of ice. You can't go there. You can't see it. It's really hard to put instruments there. So we're just doing basic research, trying to understand more about how the ice moves.
And there's another reason why we haven't gotten all the basic research done yet. We didn't know we were going to need it. We've never warmed the planet up like this before. It's another one of those no analog situations. As with permafrost, scientists are trying to predict how this ice sheet will react under conditions that have never before happened in human history. That's a challenge. But Neil Humphrey thrives on challenges.
I like solving little problems. Joel likes solving big picture problems. I like solving little detailed problems.
Neil is a glaciologist at the University of Wyoming, and I can't resist sharing that he also teaches in the Department of Theater and Dance there. I'm guessing he's one of the only people in the world to wear both of those hats. Here on the ice sheet, he's the electrician. The humming you hear in the background is the generator, which is powering some of the tools he needs. I'm looking over his shoulder as endless rows of numbers pour across the screen of his laptop.
0 plus minus 16 12
Right,
01.
right.
What is going on there?
Part of the problem here is that I designed all this. So what we're actually looking at is bad programming.
But it's kind of amazing that you can create that all. You had to basically create everything you need here.
Yeah, no, you can't buy data loggers that work in this environment on this low power and do such complicated things.
Complicated things like drilling 36 holes all the way to the bottom of the ice sheet and then sending tiny little sensors down there to collect information about temperature, pressure, and movement, which is what this team did on a previous trip to this study site. They made most of the gear themselves, set this whole system up, and then got back into the helicopter and flew away, fingers crossed that it would keep working. And it did.
Yeah, well, yeah, no, these, just sit out there in the cold and buried under the snow and floating in pools of water and things like that, and they seem to work.
It's a pretty amazing feat of engineering, and like Neil said, it's extremely detailed. He spent most of every day in the big tent where we gathered for meals, surrounded by a mysterious tangle of wires, bits of plastic, and computer chips. But despite the mad professor vibe which he seems to relish and cultivate, he doesn't come up here only to tinker with these tough little gadgets. He sees this work as a small part of a larger story.
I think a responsible society should worry about very significant things that are coming down the line. Florida is going underwater, and to know to what extent Florida is going underwater and what the time scale is, I think is actually a reasonable societal quest.
And Greenland has something to do with Florida, and explain why.
Well, Greenland is a huge chunk of frozen water that's sitting on land. If you melt it, it goes into the oceans go up, and there's no other way around it.
And when you look around the world for those huge chunks of frozen water sitting on land, this is one of the very biggest. Only Antarctica has more.
And we're talking about raising sea level 10, 20 feet. So you're going to displace hundreds of millions of people. They're going to be upset. They're going to want to go somewhere better. A guaranteed way to end up needing to fight wars is to have millions of people displaced and angry and wanting better locations, etc. From a geopolitical point of view, it seems like a disaster that one might want to avoid.
We'll have more after this short break. What were you thinking when the helicopter flew away?
I guess I'm in it now, can't back out, sort of trapped.
Welcome back to Threshold. I'm Amy Martin, and this is Rosie Leone. She's one of the 3 students on this trip. The other 2 are Aiden Stansberry and Ian McDowell. They're all in their early 20s.
Can you tell me what you're going to do?
Me?
Yeah.
Okay, so basically we are going to go out and drag this radar around to map the bed. Really not an expert.
This is Aiden. I took to calling the 3 students Team Radar because they basically had one nonstop job on the ice: map the bed.
So the bed is the rock that the ice is sitting on top of. So we're going to be walking around trying to map out so we can see what the bed looks like, which can give some insights into how the glacier's moving, I guess.
The ice sheet bed can be made up of different kinds of rock or soil or squishy layers of sediment, and it has its own geography. It can be flat in one part and hilly in another, and part of what Joel's team is trying to figure out is what happens when you combine all of those factors with the enormous weight of the ice sheet. How does the shape of the bed change how this thing moves? And a key part of the answer to that is making a map of it.
So you're dragging around radar and it's sending little signals back and forth.
Yeah, kind of. So it's kind of like if you had a string and attached to a ceiling and you flicked it, you could watch the wave go up, hit the top, and then it reflects off and comes back to your hand, kind of like that.
Nice explanation. I'm serious. That was great. Thank you. I understand now.
could be a professor one day.
And the way they get this data is to move as a unit around the ice sheet, following a mental grid. They have to walk in straight lines a certain number of meters, stop, send out a radar pulse, make sure the data gets logged, then do it again, and again, and again, in the wind and the cold, all day long.
I guess right now radar is just a little boring, so we're just like walking, placing it down.
Rosie's being nice. It's not a little boring, it's super boring, and everybody knows it. But today, Team Radar gets to take a break because Joel's taking us out to meet a moulin. Joel had given a safety talk before we got in the helicopter to fly out here, and he'd warned us about these things called moulins, holes you can fall into on the ice sheet, never to be seen again. They're pretty spooky, but they're also really intriguing portals into the belly of this beast. Because this ice isn't a solid block from top to bottom. It has an internal architecture, or maybe a plumbing system is a better analogy. There are rivers and lakes on the surface of the ice sheet, but also inside of it and underneath it. And Joel says we don't really know all that much yet about how the water moves in there and how that might affect the overall movement of the ice sheet. But as we walk out to find a moulin, I realize I have a much more basic question.
All of this ice that we're looking at, this was all once snow, or did some of the ice actually form from water a long time ago? Or?
No, this all originally fell as dry snow way up on the ice sheet, in the center of the ice sheet. 250 kilometers from here, 20,000 years ago, these little water molecules, ice crystals here, were originally snow.
And part of what makes this entire ice sheet move are the tiny little micro movements happening between those ice crystals.
Yeah, this is made up of billions and billions of grains of ice. It's crystals that are anywhere from the size of a marble to the size of a softball. Mm-hmm. And they're all sort of rolling past each other. So you can imagine when you have a stack of billions of these things and you move each one just a teeny bit past the one next to it, that's going to add up by the time you get to the top.
This is called deformation, and it's one of the two main processes of movement here. The other one is sliding, which is easier to understand. Just imagine an ice cube in a bowl, and you've pretty much got it. This team is trying to figure out how these two forces, deformation and sliding, interact in a warming world.
Think that's your moulin?
Joel's calling out to Toby Meyerbachtal, another University of Montana researcher. We're following one of the many streams that forms on the ice sheet in the summer. Beautiful clear water rushing in a winding path. And then, there it is.
Wow.
A big hole where the water is just cascading in and disappearing.
So it's safe here, but you don't want to step out there.
Yeah, don't worry.
But you can see the stream is just plunging into the glacier.
And it's plenty deep for a person to get through that.
Yeah, you would have no problem. And not only do you not want to fall in that hole, you don't want to fall in this stream anywhere because the bottom of that stream is just ice. It's completely slippery. You're just getting slid along this wet, slippery slide, and it's really hard to get yourself out.
Oh, God.
The current just carries you along until you end up in the hole.
Oy.
As we were flying into camp, we saw dozens of these streams. Some of them were more like rivers, actually, and there were tons of ponds and lakes, too.
20 years ago, there was some debate as to whether or not water could find its way to the bed of the ice sheet, this surface melt we see, whether it could even get through a kilometer of really cold ice. Since then, we've learned that it absolutely does. But now we're stuck with two new problems. One is how. We don't have that figured out entirely. And the second is, well, what are the impacts of that? What does it do to the sliding motion of the ice sheet?
Once it gets down there.
Once it gets down there.
And even though Team Radar's work is kind of boring, it's super important. Toby says they now know that there's a deep, narrow trough right under our feet, a steep ravine in the ice sheet bed.
Yeah, so you're talking about 2,000 to 3,000 feet. So, I mean, this is real topography.
It's a sort of Norwegian fjord that's right there under the ice sheet.
Yeah, wow.
And the ice there is substantially warmer than all of the holes we've drilled here.
This is something that's really puzzling them. Why is the ice in this ravine so much warmer than at the main study site? As we stand there together, watching this river of meltwater disappear into the ice sheet, Joel and Toby start bandying ideas about. It's kind of fun just to listen to them think out loud together, even though I'm only following a portion of what's being said.
The conceptual model of these things as being just vertical lines to the bottom of the ice sheet is completely flawed and wrong.
You're completely right, though. I mean, we've done the math on this. It's an easy sort of thermal problem to model. The heat moves away from this pipe source very slowly and can't warm the ice uniformly the way our data show it does.
But maybe it's not a pipe.
Oh, it goes into some sort of arterial...
Or I have another theory that there is a dragon that lives under there.
Yeah.
I leave the scientists to do their job and go off to do mine. I want to give this ice sheet a chance to be heard. There's a spot a little ways off where it's safe enough for me to lay down on my belly and put the microphone right down into a crevasse in the ice. It really does feel like there could be some sort of mythical creature living down there, or that this whole Leviathan itself could be alive. That's one of the things that makes the Greenland ice sheet so mind-blowing. It's made of this very familiar substance, but it's at a scale that's so different it almost feels alien. I mean, it's just ice, something we all keep in our freezers and drop into our drinks, but this ice cube is cartoonishly large. If you wanted to put this in your drink, you'd need a cup bigger than many countries. It's not very often that we have the chance to encounter a discrete object that's this huge, let alone hold a microphone up to its mouth and listen to its voice. Seeing and hearing all this water move around up here really brings home that I'm standing on a massive source of future sea level rise. 600 million people on our planet live in coastal areas less than 10 meters above sea level. That's 32 feet. As we warm the planet and the Greenland ice sheet melts away, a lot of those people are going to have to find somewhere else to live. This field of study, ice sheet dynamics, sounds really abstract, but the work this team is doing intersects with questions that have huge moral implications for people and ecosystems around the globe.
You know, if it takes 3 or 4 millennia to get a large amount of melt from Greenland into the ocean, that's a completely different societal issue if it's only a century or 2 or 3.
Imagine if 600 million people need to relocate in 50 years versus 500. That's why we need to figure out how and how fast this giant ice cube could move.
The climate system itself is driven by ice. Even if you live at a southern latitude somewhere, if there's big change in the poles, it will impact how the climate system works, and it will ultimately work its way down to impacting you.
Falling in love with the Greenland ice sheet is an emotionally risky proposition right now. But what can I say? Love isn't logical. And as anyone who's ever fallen in love knows, timing matters. We still have a chance to save this ice sheet from the worst, but that window of opportunity won't stay open forever.
Production partners for Season 2 of Threshold are Montana Public Radio and PRI's The World. Our reporting was funded by the Pulitzer Center on Crisis Reporting, the Park Foundation, and by you, our listeners. You can support our show and see pictures from the ice sheet at thresholdpodcast.org.
Threshold is made by Nick Mott, Rachel Kramer, Cheryl Skibicki, and me, Amy Martin, with help from Frank Allen, Jackson Barnett, Josh Burnham, Michael Connor, Rosie Costin, Matt Hurley, Rachel Klein, Zoe Rome, Nora Sachs, Maxine Spire, and Zach Wilson. Special thanks to Robin Abbott and to this whole team of scientists for letting me tag along on the ice sheet for 5 days. That's Joel Harper, Neil Humphrey, Rosie Leone, Ian McDowell, Toby Meyerbach-Tall, and Aidan Stansberry. Our music is by Travis Yost, and I want to note that I sent Travis that recording from the inside of the ice, and he created this song you're hearing around it. So this is a collaboration between Travis Yost and the Greenland ice sheet. And in our next episode, well, our next episode is our last episode for this season. See you then.